Good.
Yes, please.
So, A, the monkey climbs up with an acceleration of 6 meters per second squared. Then B, climbs down with an acceleration of 4 meters per second squared. And then C, climbs up with uniform speed of 5 meters per second. And D, falls down the rope nearly freely under gravity. So these are the 4 situations. We want to see among which of these situations can the rope break. This is a tree, so this is the support of the rope. This is a monkey. I'm here drawing. But there's a monkey. We are told that the tension, the maximum tension in the rope is equal to, so T max is equal to 600 Newton. And the mass of the monkey is 40 kilograms. Mass of monkey, 40 kilograms. Of course, gravity is 10 meters per second squared. Now, in the first situation, the monkey climbs up with an acceleration of 6 meters per second squared. Class, whenever there is an acceleration, every acceleration must be caused by what? Every acceleration must be caused by what? Akosia.
Change in velocity.
Not in the case of, fine, yes, change in velocity, but with regards to Newton's for laws of motion, you can also connect every acceleration. Every acceleration must also be caused by what? Kenneth?
That is a force.
A resultant or net force, resultant force, or an unbalanced force. So there must be a force or a resultant force. Okay. So whenever there is an acceleration, don't forget Newton said that the external force is directly proportional to the acceleration. So if the external force or the resultant force is greater, acceleration would also be greater. And this is the basis on which this question lies. This is the basis on which the question lies. So the direction of the tension in the string is here. The weight of the monkey would act downwards, mg or w. Okay, once the monkey is climbing up, the tension must be greater than the weight. Once the monkey climbs up, so once monkey climbs up the rope, the tension in the string must be greater than the weight for the monkey to be able to climb. So T must be greater than W. Let me change the weight to mg. So the net force net force acting on the monkey would be equal to the tension, which is greater, minus the weight, which is mg. Please, are you okay up to this point? Are you okay up to this point? Give me feedback. Are we all okay up to that point?
Yes, please.
All right. So if the net force is this, then Newton is saying every resultant or net force is equal to mass times acceleration. So we equate the resultant or the net force to this. So T minus mg would be equal to m times A. So that we are looking for the tension and compare it with the maximum tension in a string. So T therefore will be equal to mg plus ma. Okay. And so therefore T will be equal to m out 40 times 10 plus, in the first situation, we are talking about an acceleration of 6 meters per second squared. 6. And so we have 40 times 16. And what is 40 times 16? Yes, Kenneth. Pardon?
640.
This is
640.
640 Newton. So it means that when the monkey climbs, accelerate up, this will be the tension within the string. Now, if this is the tension, when you compare it with the maximum tension, then it tells you that when the monkey accelerates up the string, it will surely break the rope, because the tension when the monkey accelerates with this magnitude up will be greater than the maximum tension in the rope. So therefore, the rope breaks in this situation. Oh, yes. Okay. When the monkey accelerates up the rope, with this amount of acceleration, the rope will break. Because when we calculated, we have our tension greater than the maximum it could bear. Please, any question? Any question?
So please, why is it that when it's climbing up, Mr. Dia, please, why is it that when it's climbing up, the tension is greater than the weight, and not the other way around?
If the weight is greater than the tension, the rope will tear straight away. It will not be able to climb. It is like when I tie a rope to a support and suspend you a queer, and your weight is greater than the tension within the string, what will happen? It will just tear off. Okay, so for the monkey to be able to climb, then the tension must be enough to support the weight. So the tension must be greater than the weight. And if they are equal, then it means if the tension is equal to the weight, then there's no need of this acceleration A. Because when the net force is 0, there's no acceleration. Okay, are you okay?
Yes, sir.
All right. Then let's look at the second situation. Fine. The first situation has given us the answer, but let's understand why the B, C, and D will not also work. The second is that when the monkey climbs down with an acceleration of 4 meters per second squared. So this time we are looking at the monkey climbing down. So B, monkey climbing down with an acceleration of 4 meters per second squared. So this time the direction of motion of the monkey is down. Okay, so it must be it must be the other way around. The net force will be equal to its weight mg minus the tension, because the direction is towards climbing down. So its weight must be greater than the tension to enhance this. So mg minus t. Okay, are you okay?
Yes, please.
So when you substitute ma for this, you have mg minus t. T therefore would be equal to mg minus ma, and m out, g in minus a would give us a mass of 40, then gravity 10 minus acceleration of 4. So the tension in the string would be equal to 240 Newton. And when you compare the tension when the monkey accelerates down is less than the maximum tension within the string. And so string or rope will not break. So since 240 is less than 600, rope will not break. Then the C question is that C, when monkey climbs up with uniform speed of 5 meters per second. So here, the question to ask yourself is that when a body moves with uniform speed, what happens? When a body moves with a uniform speed, what happens?
So please, there is no acceleration.
There is no what?
Acceleration.
Or there is no acceleration because of what? Because?
So please, because the net force is 0.
Exactly. Dynamic equilibrium. There is no acceleration because the net force is 0. So these are the basic things we need to understand. So over here, because what is the direction? Consider moving up. So over here, T must be equal to mg, dynamic equilibrium, or T minus mg must be equal to 0. There's no net force. So straight away, the tension is equal to 40 times 10. And this is 400 Newton. when you compare, it is less than the resultant, the maximum tension. And so string will not break or rope will not break. Then D. As for D, the monkey is even falling freely from the rope. The monkey is falling freely from the rope. Okay. So if the monkey is falling freely from the rope, its weight minus the tension must be equal to the net force acting on the body. But what is the net force acting on the body? Mg. Force of gravity. And the force of gravity will be equal to the mass of the body times acceleration due to gravity. So you realize that the tension T will just be equal to 0. Okay, it is falling freely from the rope. So the net force will be its weight minus the tension must be equal to the total force on the body. And what's the total force? Force of gravity. Force of gravity on the body would be equal to mass times acceleration due to gravity. So when you subtract, you have the tension to be equal to 0. Okay, so when the tension in this case is equal, it means the tension acting in this situation is just not there. And so the maximum tension is what is there. So it will certainly not break. So these are the 4 different situations of the question. If you are okay, if you have any question, ask. If you don't have any question, then we move on to our circular motion question. Do we continue? Today we are going to look at centripetal force. All right. Can I clean the board? Do I clean the board?
Yes, please.
All right. We go to centripetal force. So, Bino, are you okay with the solution? Obinowa.
Yes, please.
But Obinowa, did you understand the question or you saw it somewhere?
Please, my elder brother explained the concept to me.
Yes, but I think where in one of them where you made the acceleration negative and all that, can you explain it? Okay. All right, maybe another time. So centripetal force. In JHS, you were talking about, I think you were learning the definition of centripetal force by rote, 2 and 4. So, Mami Araba, what is centripetal force? Mami Araba, what is centripetal force? Hey. Adwa Asante Otubia, recall your JHS definition of centripetal force.
Yes, I remember the centripetal force is the force that keeps an object moving in a circular path.
Okay, thank you. So Whenever a body is in circular motion, there is always a force that keeps it towards the center in order to help the body maintain its position within the circular part. So whenever a body is in circular motion, there is a force which always ensures that the body stays within the circular part. Okay, and that is centripetal force. So we define this as the force which keeps a body moving in a circular motion within the circular part. Now, centripetal force. So centripetal force is responsible for keeping bodies within the circular part. Now, one other quality of centripetal force is that it is always directed towards the center. Center of the circle. So it is always directed towards the center of the circle along the radius. Along the radius of the circle. Because of this, centripetal force is also sometimes called radial force. It is for this reason why centripetal force is also known as radial force. Radial comes from radius, so its direction is always towards the center. F centripetal is towards the center along the radius of the circle. In fact, the word centripetal is a Greek word. The word centripetal is a Greek word meaning center seeking. So by its name, we can deduce that centripetal force is a force that is always seeking the center. So the word centripetal is a Greek word which means center seeking. So it's a center seeking force. Are you done writing? Now, This kind of circular motion, in fact, we are discussing, is actually limited to uniform circular motion. We are only looking at uniform circular motion. And when the body is moving in a uniform circular motion, it simply means that the body moves within the circular part with constant speed, with constant or uniform speed. V. So a body in a uniform circular motion moves with a constant speed. Its speed is constant within the circle. Please, are we okay? If you are done writing, let me know so we could continue. Are you done?
Yes.
Okay. Now, let's try to understand what causes centripetal force. What actually causes centripetal force? The cause of centripetal force. What causes it? The cause of centripetal force. Let's assume this body is in circular motion at a point A. The body starts from a point A, and within a small time interval B, delta T, the body has moved from A to B. So it is moving, but we are only considering the body moving from a point A to B. And don't forget, in every circular motion, the linear displacement delta S is directly proportional to the angular displacement at the center. So A to B will give us a linear displacement delta S and then angular displacement delta theta. We are looking at small angular displacement. So the linear displacement is delta S, then the angular displacement is also delta theta. Now, when the body is in circular motion, at every point, its direction is changing. So let's take 4 points along the circle. When the body is here, its direction is towards the side. So its uniform speed V is here. When it gets to this point, its direction is here. When it gets here, its direction is here. When it gets to this point, this is its direction. So at every point, the body's direction is changing. If the body's direction is changing every time, then though the body is moving at a uniform speed, because of the changing direction, its velocity at every point will be different. Because assuming this is A and B, this is the direction of A, this is the direction of B. So within the point A and B, the direction is changing. So whenever we have a body moving with a constant speed, but a changing direction, it will automatically cause the velocities at the point to change. What is velocity? Either change in displacement with respect to time, or velocity is also a changing direction with respect to a uniform or constant speed. So whenever the speed is uniform or the same, but the direction is changing, it can amount to different speeds. Please, are we okay? Sorry, different velocities. So because of the changing direction, the velocity at A will be VA. The velocity at B would also be VB. So over here, even though the body is moving at a uniform speed, let me write that for you. A very important point. That even though the body moves with a constant speed, however, due to the changing velocity, changing direction, the velocity of the body at any two positions changes. So the velocity is changing because of what? The changing direction. The velocity of the body is changing due to the changing direction. So even though the body is moving with a constant speed, however, due to the changing direction, its velocity at any 2 points would also change. Are you okay? Are we okay with this point? A very important point under centripetal force. Okay. Now, when the
Please, I have a question.
ask your question.
Please, the velocities. I want to know, is it only the linear velocity that changes, or both the linear and angular velocities change?
Here, we are looking at a change in the linear velocity, of course, would affect the angular velocity at the center. So if it has a changing velocity at this point, definitely it would affect its angular velocity. All right. But over here, we are looking at what happens to the velocity as the direction changes. We are not talking about the angular velocity at the center. Okay. So this changing velocity, let's look at, let me draw. The point is that this velocity at A makes is tangential to the circle. When a quantity is tangential to the circle, what happens is that it just touches the circle in such a way that the body touches the circle in such a way that the angle between the radius of the circle to that quantity which just touches the circle is perpendicular. So whenever you have a line touching a circle, okay, in a manner that it makes an angle of 90 degrees with the radius, it means this quantity, if its velocity is tangential to the circle. So when we look at, if we look at the individual VA is tangential to the circle, meaning it makes an angle of 90 degrees with this radius. When we look at VB is also tangential to the circle, and so it also makes an angle of 90 degrees with the radius. So this is what happened when the direction is changing, and so the velocities are different at point A and point B. Okay, the velocity there is always the linear velocity at each point is tangential to the circle. Now, if the velocities establish this relationship with the circle, if we use geometry, we can deduce that then the angle between the two velocities VA and VB is equal to the angular displacement at the center. So this angle at the center is also equal to delta theta. Let me redraw the velocity somewhere here. So we have VA and VB. We also have VA in this direction. VA, VB, because VA is perpendicular to the radius and VB is also perpendicular to this radius, the angular displacement is the same as the angle between the velocities VA and VB. So if this is theta, delta theta, this is also delta theta. At your level, I think I'll shorten certain things for you so that as, as you are growing, then I'll be bringing it. Else, if I do a lot of them with you at this level, you may lose interest in what I'm doing. So I'll just do something and then give you the formula. If I'm proving with you, I'm telling you, you would develop a bad attitude to this. So now in vectors, you have two velocities, VB and then VA. VB, VA. If we draw another vector here, maybe unknown, X, by triangular law of vectors, looking at the directions, we can argue that, okay, VA plus the unknown must be equal to VB. Please look at the direction. So by triangular law of vectors or triangle law of vectors, we can argue that, oh, okay, then VA plus the unknown vector X must be equal to VB. If we take the direction, do this. Then if we also decide to change the direction this way, we can equally argue from the same principle that VB plus VA plus the unknown is also equal to VA. Or we can also argue that Akosia.
You say, yeah, is it not the square of VA plus the square of X?
No, by triangle law of vectors, we are following the direction of the vector quantities. We are not looking at the magnitude yet. Okay. By triangle law of vectors, we can argue that VA plus this is equal to VB, or VA or VB plus X is equal to VA. By triangle law of vectors, we can argue this out. And with triangle law of vectors, we are not looking at the magnitude. We are only following the directions to make sense out of it. Akosia, are you okay?
Yes.
Now, because of a special reason, we don't consider this, but we always take the direction towards this side, which you understand later. X. So if we use the first one, that's VA plus the unknown is equal to VB, then when we make X the subject, we have VB minus VA. And VB minus VA is equal to the change in velocity, delta V, between B and A. So delta V is equal to VB minus VA. That's the change in velocity between VB and VA. That's the meaning of VB minus VA, the change in velocity between B and A. Are we there? Now, in
Mr. Dear,
Equia,
please, he said it's uniform. It has like it is uniform. So why is there a change in?
uniform speed. We are looking at originally, we have the body moving with the uniform speed, V. However, due to the changing direction, the velocity will change at any 2 points. Okay, so ideally, what we are saying, we are looking at this body moving with the uniform speed, but because of the changing direction, the velocity at any 2 points will change. That's what we are saying. Are you okay?
Yes, please.
So the changing direction creates the changing velocity at any 2 points. I'm not still talking about speed. The changing direction, even though the body is moving with a uniform speed, but due to the changing direction, the speed also changes at any 2 points. The reason for us having a change in velocity, not a change in speed. Right? Then in physics, whenever there is a change in velocity, there will be acceleration. Whenever there is a change in velocity within a given time, there will be acceleration. So what it simply means is that the change in direction brings about an acceleration. The changing direction causes a change in velocity. The changing direction causes a change in velocity. And whenever there is a change in velocity within a given time, there will be acceleration. So consequently, the change in velocity also causes an acceleration. The reason is that acceleration is the change in velocity with respect to time. So this is the build-up. The build-up is that, yes, the body is initially moving at a uniform speed. but due to the changing direction, the velocity at any 2 points also changes. Okay, now this velocity, change in velocity at any 2 points also brings about different velocities at any 2 points also brings about a change in velocity delta v. And once there's a change in velocity, there will certainly be acceleration. Now, if we are to go further, you realize that this acceleration, are we listening? If we are to, as I said earlier, I don't want to bother you so much with this technical explanation because of your level. But what I'll tell you is that if the change in velocity delta v also, if we are to go into it deeper, has a direction towards the center. So let me clean this side of it and then write that for you. The change in velocity delta v has a direction toward, don't forget velocity is a vector quantity. So it has magnitude and then direction. As you grow, I will explain this with that diagram and mathematical term. For now, if I should do so, in fact, you won't enjoy. So the change in velocity delta v, which is actually equal to vb minus va, has a direction towards the center of the circle. So has a direction towards the center of the circle and along the radius. This is the direction of the change in velocity. Please give me a minute to pick this call and then get back to you, okay?
Okay.
Okay, so the delta V, the change in velocity, has a direction towards the center and along the radius. Okay, now, because of the change in velocity, we have an acceleration, because acceleration is equal to delta V over delta T. I earlier told you that this movement occurs within a time, small time delta V. Okay, and so the change in velocity VB minus VE over T. Okay, so the change in velocity will also bring about an acceleration. Okay, the direction of the change in velocity is also the direction of the acceleration, because the change in velocity is a scalar vector quantity. We have identified its direction towards the center along the radius. Delta T, time is a scalar quantity. So once this is a scalar quantity, this is a vector quantity, the acceleration naturally takes the direction of the vector quantity, which is delta V. Class, are you with me? Are you with me here?
Yes, please.
So the acceleration caused by the change in velocity also has direction towards the center and along the radius. Because of this acceleration also bears a special name. And the name is that we call the acceleration also as centripetal acceleration. Centripetal acceleration. Meaning center seeking acceleration. Okay, center seeking acceleration. This center seeking acceleration is given by the formula the square of the speed v squared over the radius. So the acceleration which is directed towards the center is equal to the square of the initial uniform speed v over the radius. Okay, this formula is provable, but I don't want to bore you today with a lot of proof. Okay, when you come to school, I can take my time and take you through. Kenneth and Immaculate, when I come to your end, I'll prove it for you. But for today, I'm giving it to you. The acceleration, which is caused by the change in velocity, okay, has a direction towards the center. And because of this reason, we call this as centripetal acceleration or radial acceleration. So in some books, you'll see this as AC or AR. Okay, either because along the radius, we can also call it as radial acceleration because it's directed towards the center, centripetal acceleration. And its formula is the square of the uniform speed V over the radius of the circle R. Please, are we okay? Akosia Benewa, Immaculate, Mami Arabai. Oh, I wish I can mention her. Are you okay?
Yes, please.
All right. Now, the last part. Another formula for this is that, you see, linear speed or velocity V is equal to R times omega. And so we can substitute V for this and expand this. R omega all squared over R. And the centripetal or radial acceleration will be equal to omega squared R. Another formula for the centripetal or radial acceleration. When you square this, you square this, so it will cancel and will be, okay, let me take my time, do it gradually for you to appreciate well. So we have R omega all squared over R. This is equal to R squared times omega squared over R. And so AC or AR is equal to omega squared R. Another expression for centripetal acceleration or radial acceleration. Now, every acceleration is caused by a net force. The beginning part of what we were solving. Every acceleration is also caused by a net or resultant force. So if there is an acceleration towards the center, then there must be a resultant force which causes this acceleration. Okay, because every acceleration is caused by a net force. So we try to get a relation for this resultant force or net force which causes the acceleration. So because every acceleration is caused by a resultant force from Newton's second law. F resultant is equal to mass times acceleration. So we are interested in this resultant force which causes the acceleration. And so F is equal to mass times the centripetal acceleration, because the centripetal acceleration is actually caused by a resultant force. So M times V squared over R is the formula for centripetal force. The direction of the acceleration is the direction of the resultant force. So the centripetal force is also directed towards the center of the circle along the radius, hence centripetal force or radial force. So in actual fact, circular motion is caused by a centripetal force. It's a centripetal force which causes the circular motion. But because every acceleration, I said centripetal force. Circular motion is caused by centripetal acceleration. But because every acceleration is caused by a force, that is why we give the force which keeps the body in the circular path to centripetal force. Another way to express centripetal acceleration is using the other formula, omega squared. When we substitute A for omega squared R, we have M omega squared times the radius to be another formula for centripetal force. So either you express it as 1 or you express it as 2. Both ways have relation for the centripetal force. Please, are we okay? Please, if you have a question, ask. So circular motion is actually caused by centripetal acceleration. But because every acceleration is caused by a force, the reason for adding centripetal force to all that we do. And centripetal force is given by mass of the body times the square of the uniform speed over the radius. In some other situations, this relation can also be modified. We can also remodify this in a different form. And this is it. Because angular speed is equal to 2 pi over time, we can also say that centripetal force is equal to M times 2 pi over the period, capital T, squared times R. Please here, be careful you don't take capital T to be the tension. It's period. So we can equally have 4 a square of 2 square pi squared mass times radius divided by the period squared. So it's just a matter of substituting angular speed and you'll be smiling. Please, I'm coming. Facebook wants me to confirm some Zoom. Now, let's look at applications of centripetal force. How can we apply? So I'm coming. Before the let me draw something for you. So the whole thing is that it's like a body is moving in this direction. But due to with a speed v, but due to the change in its velocity, due to delta v, its direction changes from here and then comes here. Okay, the same body is going here. But due to a change in its velocity, its direction changes due to a change in velocity delta v. The direction changes from going straight to this point. The same body will want to go straight, but due to a change in velocity, its direction changes from going straight and then comes here. Okay, the body wants to go this way. Due to a change in its velocity, its path changes from this side and then comes here. Due to the delta v. It wants to go straight. Due to change in velocity, it changes and then from going this and then comes here. So when you go through it throughout, you realize that the bodies, because of the change in velocity, the body describes a circular path. So due to the change in velocity, the body will describe a circular path. If there is space and I do it all along, you realize this will give me a circle. Okay, so the change in velocity actually causes an acceleration, which is centripetal acceleration directed, okay, towards the center. So as a result of the change in velocity, blah, 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 the body will describe a circular path. All right, applications of centripetal force. Whenever a body is in circular motion, then it means there must be a force which is responsible for keeping it within the circular path. So applications of circular motion. Now, circular motion can be exhibited by one. When a stone is tied to a string, a string or thread, and weld. So when you tie a stone to a thread and weld, it describes circular motion. Once it describes circular motion, then it means that there must be a force, a centripetal force, which keeps the stone within the circular path. So in this case, what provides the centripetal force? So we said that the centripetal force Fc, when a stone is tied to a string and weld, is provided by the tension within the string. So the force, the tensional force in the string provides the centripetal force. That is why when the string breaks, okay, it is thrown away. So we said M centripetal force mv squared over r is equal to the tension in the string. Another application of this is, please take note that here the radius of the circle is equal to the length of the string. Let me get something to demonstrate this for you. Wish I have something to demonstrate. Good. Look at this. This is the length of a string. Let's assume this is the mass. Now, when I tie and then whirl, the length of this is the whole length of the string from the mass to where my hand is the length of the string. If this is in circular motion, meaning the fixed point is my finger over here, the body would have to go this way. It will describe, okay. I don't know if you can see properly. Let me bring it to the board. If I have this is the mass and it is describing circular motion. This is how it will go. So by moving this, the mass is describing a circular path. My finger is the center of the circle. Okay. So in a situation like this, you realize that the center of the radius of the circle is equal to the length of the string, because the radius is from where my finger is to where my other hand holds as the mass or the weight. So when it is describing a circular path, the radius of the circle is equal to the length of the string L. Please, are we okay? Are you okay with the illustration?
Yes.
So for when an object is tied to a string and weld, the radius of the circle R is equal to the length of the string L. Hence, R is equal to L. Another application of circular motion is this. When a car negotiates a bend, or curve, the centripetal force which keeps the car in the circular orbit I'm coming. So when a car negotiates a bend, the centripetal force which keeps the car within the bend or curve is provided by the tension, the frictional force between the road and then the tires of the car. So when a car negotiates a bend or curve, the centripetal force is equal to, so centripetal force in this case is equal to the frictional force between the rod and the tires of the car. So if this is what provides the centripetal force, then we can say that mv squared on r is equal to friction. And frictional force is given by mu times the reaction. Coefficient of static friction times the reaction. Now, because R is given by mass and gravity, we can also equate this to mu mg. If this is mu mg, mass of the body, let's make V the subject. Help me make V the subject. Yes. Help me make V the subject. Any one of you.
V is equal to the square root of R initial.
So V is equal to the square root of mu Rg. This V gives us the formula for, or the expression for, maximum speed of a car negotiating a bend. V is equal to the maximum speed of a car negotiating a bend. Inshallah, are you there? Inshallah, acquiring.
Yes, please.
Okay, so the expression for maximum speed of a car negotiating a bend. What does this mean? It means that when a car is moving within a roundabout or a bend, its maximum speed depends on the maximum possible speed that driver can be moving within the bend depends on two factors. The factors are that one, the speed V is directly proportional to the square root of the coefficient of friction, mu. The speed V is also directly proportional to the square root of the radius of the curve. As for gravity, it is constant. What is mu? Mu has to do with the nature of the surface of the road. When the road is, if mu is high, then it means the road surface is very, very rough. If the value of mu is greater or larger, it means the surface of the road is very, very rough. If the value of mu is so less or small, it means the surface of the road is so smooth. So the value of mu informs friction. Okay, when mu is high, the value of mu is greater, it means frictional force is also greater on the surface. If it's less, friction is less. So the maximum speed a driver can embark on a curved road or bend depends on the nature of frictional force or friction on the surface of the road. The maximum speed is also directly proportional to the radius of the circular path. When the radius is large, the speed can also be large. If the radius is small, then the speed drivers embark on must also be small. It is for this reason that Ghana Road Safety Commission has a campaign that whenever it rains, drivers must reduce speed. Whenever it rains, drivers must reduce speed, because when it rains, it reduces the value of friction, meaning that mu, coefficient of friction, decreases. And so if mu is decreasing, velocity depends on mu, and so you must reduce speed. So the maximum speed V max for the car to safely negotiate the bend must be any value less or equal to the square root of mu rg. Okay, this is for motorists or drivers to safely negotiate a bend or curve. For motorists to safely negotiate a bend, the value of V must be less or equal to square root of mu rg. If it is if V max is greater than mu rg, the car skids off from the circular path or skips off from the bend. What do we mean by skips off? Apia, what's your question?
Mr. Please, you've answered it. Sorry.
Okay. If a car skids off from a circular path, it is moving and would have to stay within the circular path. If it skids off, it means it is moving straight away. It will move off from the circular path and go straight to hit something. Meaning it will follow the direction of the linear speed v instead of following the direction of the change in velocity associated with it. Okay, so for the body to stay within the bend or circular path, the maximum speed must always be less or equal to this. If V max is greater than this, the car skids off from the bend. All right. Okay. Let me get a question so that we can apply it to what we have learned so far to solve, right? I'm looking for a question on okay, a first question. Are you ready? I'm dictating. Are you ready? An object of mass 0.25 kilogram has a control wire of length 2 meters. An object of mass 0.25 kilogram has a control wire of length 2 meters attached to it. The other end is held in the hand. The other end is held in the hand, and the object is well in a horizontal circle. And the object is well in a horizontal circle with a speed of 20 meters per second. Well, in a horizontal circle with a speed of 20 meters per second of radius 2 meters. Of radius 2 meters. Calculate the tension in the wire. Calculate the tension in the wire. So 2 minutes, you must give me this answer. One, so calculate. Okay, when you finish, calculate the tension in the wire. When you finish, I'll give you another question. This is about 2 minutes work. 2 minutes, even more. Are we true?
Say, please, an object of mass.
The mass is 0.25 kilogram. Has a control wire of length 2 meters attached to it. The other end is held in the hand, and the object is swelled. The object is swelled. This is the spelling of swelled. And the object is swelled in a horizontal circle with a speed of 20 meters per second. A speed of 20 meters per second of radius 2 meters. The speed of 20 meters per second of radius 2 meters. Calculate the tension in the wire. Yes, who is true? Who is true?
Sir, please, I got 14 Newton.
You got what?
14 Newton.
Look through it again. Your mass is 0.25 kilogram. The length of the wire is 2 meters. The speed is 20 meters
So
per
please, I have 50 Newton.
The answer is 50 Newton. The answer is 50 Newton. Are we there? So this is tension in the string is equal to the centripetal force, or the centripetal force is provided by the tension in the string. So when you calculate the centripetal force, mv squared over r, it is equal to the tension. Question 2. Question 2. An object of mass 50 kilogram, an object of mass 50 kilogram moves round a circle of radius, 6.0 meter with a constant speed of 10 meter per second. With a constant speed of 10 meter per second. Calculate I, the angular velocity. I, the centripetal force. I, calculate the angular velocity. Then I, the centripetal force. Maximum 2 minutes. You must do it. Mamia, but so you can't hear. Person by review. Okay, an object of mass 50 kilogram moves round a circle of radius 6.0 meter with a constant speed of 10 meter per second. An object of mass 50 kilogram moves round a circle of radius 6.0 meter with a constant speed of 10 meter per second. Calculate I, the angular velocity. I, the centripetal force. So what have we had for the angular velocity? I want everything, the value and then the units must be correct. Bento.
Studio, please there.
That what?
I had the angular velocity to be 1.67 radian per second square,
Correct for 3
and
points.
centripetal force to be 833.3 Newton.
8.
33.3 Newton.
Sorry, 1 out of 3.
Sir,
Mm-hmm.
sir, please, the unit she mentioned, she said radian per second square.
For what?
The first one, she said radian per second square.
What? I asked you to calculate for the angular velocity, so
So
I
I got
didn't-
1.67 radian per second.
it's radian per second, yes. This is angular velocity. Then the second question.
Sir, please, the centripetal force, I got 833.33 Newton.
5 times 100 over 6, right?
Mr. Dia, please, you gave us 50 kilograms.
Yeah, it was 50 kilograms.
The mass is 50 kilograms. Let me confirm.
Yes.
Oh, okay then. the answer in the book rather. So 50 times 10 squared. So 5,000 divided by 6. Okay. Okay. You are correct. Then the last question. Please, I hope you are all.
Miss Adrian,
Hello.
for the angular velocity, can you use omega is equal to velocity out of radius?
Oh, that's what you must you must use.
Okay. And the velocity is 10 meter per second, and the radius is 6 meter.
Yes.
So once you have 1.67,
That's the answer. That's the answer.
no, I'm talking about the units.
The units, don't worry your head. See,
So you can
once
put a unit.
listen, with the unit, once all other quantities, velocity and radius is in SI units. Velocity meter per second, radius in meter. When you divide, the angular velocity must automatically take its units, radian per second. Okay.
So you can't put.
So you don't worry yourself as to how you are going to get radian per second. All that you must know is that all other values must be in SI units, and you express the angular velocity in its SI units. That's all.
So you can't put revolution per second.
No, when the speed is in meter per second, the radius is in meter. When you divide V by R, it must be in radian per second, because all other variables or factors are in SI units already. All right. So the last question. A 1,500 kilogram car. A 1,500 kilogram car moving on a flat horizontal road. Moving on a flat horizontal road. Negotiate a curve. Moving on a flat horizontal road, negotiate a curve. If the radius of the curve is 35 meters, if the radius of the curve is 35 meters, and the coefficient of static friction, between the tires and the road is 0.50, and the coefficient of static friction between the tires and the road is 0.50. Find the maximum speed. Find the maximum speed for which the car can turn successfully. Find the maximum speed for which the car can turn successfully. That's a problem. Please take gravity to be equal to 10 meters per second squared. Mishra, what have you had? Mishra? Inshira? Adwa? Mami Araba, uhuye bufu.
Yes, please.
Mami Araba, a 1,500 kilogram car moving on a flat horizontal road negotiates a curve. If the radius of the curve is 35 meters and the coefficient of static friction between the ties and the road is 0.50, and the coefficient of static friction between the ties and the road is 0.50, find the maximum speed of the car for which it can turn successfully. What have you had? I'm not saying, may your online class, may you are not my friend, right?
Miss Lydia,
So,
please, I got the velocity to be 13.228.
23. So approximately 13.23 meters per second.
Yes, please.
Nice one.
Say,
Yes, can it?
that is the velocity should be less or equals to 13.228.
So it means for the car to still turn successfully, we must be anything less or equal to 13.23 meters per second. So that's correct. So class, I think this is one of the ways to apply what we've learned for today. I'll look for some challenging questions as well so we can apply. But we also would have to talk about planets orbiting the sun and all that, okay? So if you have any question, ask. If you don't have any question, then this is where I draw the curtains on today's meeting. Any question? Akuya?
No questions, sir.
Okay, then good night to all of you, okay? Good night to all of you. You won't mind me. Hey, Arias.
Please, good night.
Bye-bye.